current radiation, and C is the partner of the current radiation that is falling into the black hole. Okay. So now, imagine that the black hole is formed from the collapse of some pure state. Okay. And so now the key is to examine the entanglement entropy or the von Neumann entropy of the system A. Okay. And so that's defined as usual as just minus a trace of rho A log rho A. And it's important to recognize that even at the beginning, there's no A to start with because there's nothing that's been emitted. So at the beginning, you just have the black hole and you have some empty space, and therefore this von Neumann entropy is 0 at t equal to 0. Now at the end point of Hawking radiation, when all the black hole has been converted into Hawking radiation, then if the system started with a pure state and you believe that unitarity holds, then the system ends up in a pure state. Okay? And therefore at t equal to t lifetime, which is at the end of Hawking evaporation, okay, the entanglement entropy of A is 0 again. So are these statements clear? Is there a question about this? Okay.
Well,
yeah.
Whose time is t?
Whose time is t? So this is good. So t is the time of some observer sitting outside. So some observer sitting outside, and he forms the black hole, and then at the beginning there's no radiation, and then at the end, after time of evacuation, is evaporated. So it's the end of evaporation for some observer sitting outside, and he says, I say it's 0. I'm not putting any numbers here, so it's just 0 and end of that. Okay, good. Now, in fact, you can say more. You don't have to fix only the endpoints. You can say more about what this entanglement entropy is. And this is something that was done by Page a long time ago, in fact, more than 20 years ago. And what Page did was, he analyzed what happens if you take a big system and you break it up into two parts. Okay? And he found that if you take this big system and you average over it using the hard measure, in fact, you can say, you can make some very precise statements about the entanglement entropy of one part of the system to the other part. And if you think of this black hole evaporation as some big system that's being separated into two parts, which is the old radiation and the rest of the black hole, then in fact, for a generic state in the full Hilbert space, you can fix the shape of this curve very accurately. And you find that this curve basically goes up linearly up to some point, which is called the Page time, and then it goes down linearly up to this t finally. So in fact, not only can you say that it's 0 here and 0 there, you can in fact fix the entire shape of the curve to show that it goes up smoothly and then it goes down. I've rescaled time to make these two parts equal, but the fact that it goes up linearly and comes down linearly is very robust. Or goes up monotonically and comes down monotonically is very robust. So this is a very robust statement, which just comes by some general arguments by taking a big system in a big Hilbert space and dividing it into parts. Okay.
The dimension of A changing, the Hilbert space associated with A changing with time, and this is the entropy associated to.
Yes, that's right. I mean, you can formulate it in a Hilbert space of fixed dimension, which you populate slowly.
And sorry, what do you mean exactly by hard measure?
What do I mean by hard measure? So you take a Hilbert space and you take some basis state and you write every state as unitary acting on the basis state. You write down the measure of the unitary group. That's the hard measure.
How much is complex?
So this is a finite dimension.
Yes. But we can study, we can use complex measure to study field theory.
We can use what measures?
Complex measure. Because how measure is complex? Well, usually use non-complex.
Oh, good. So you have to put some cutoff on the set of states. So for example, if you formulate the theory with some infrared cutoff, then you have a finite number of states. You can use that to do this. There may be a subtlety there, but it's a subtlety about infrared cutoff. So you put infrared cutoff. There's a natural UV cutoff because the black hole has finite energy. So you get a complex space. Okay. Now consider some black hole which is beyond its Page time. Okay, so it's in the part of the curve that's decreasing. Now for a black hole of this kind, it must be the case that SAB, okay, is smaller than SA. And the reason for that is because B is going to go and join A. So A at time t plus delta t is A plus B. Okay? Because B is the radiation that's just being emitted, and therefore A at t plus delta t is basically A, whatever A is at t, plus the pair plus the particle that's being emitted. Yeah.
Sorry, this previous computation of Pages, why can't that be thought of as a resolution to the old information factor?
Why can't this be thought of as a resolution to the old information factor?
Unitarity.
This is a statement about what the expectation would be if unitarity holds outside.
And this is in contradiction with Hawking's computation.
well, if you took Hawking's computation seriously, then it's in contradiction with Hawking's computation, because Hawking's computation would go up and keep going up because it's just thermal. So if you really took Hawking's computation seriously, which as I said you shouldn't, because entanglement entropy is a fine grained measure, but if you believed it was it was linear, then it would go up here and just keep going up, up, up.
But is this correct?
Well, this is what is correct if quantum mechanics is correct. So this is the expectation. I'm going to show you a paradox with this, but this is the expectation. I mean, this is correct, but this is the expectation. Hawking's calculation is linearly just all the way. Okay. So now, if you say that okay, so if you look at the black hole beyond the space-time, you see that SAB, because that's S of A at T plus delta T, so it's S of A at the next step, is smaller than SA. That's because the entropy is decreasing. Second, you look at these systems B and C. So remember, B is the Hawking particle just outside the horizon, and C is the particle just inside the horizon. And because B and C are related to the Boguslavov transform, the vacuum for the infalling observer, these two are basically together in some pure state. Okay, so what's happening is that you have pair creation, but if you look at both particles together, then these two are in some pure state, and therefore you can say S of BC is 0. That's the statement that the black hole is emitting Bell pairs. It's emitting 1/2 of a Bell pair. So if you look at that guy and his partner, then those two together are 0. And this is basically the statement that the horizon is locally like flat space. Of course, you have just Hawking's calculation, which tells you that each of the individual pairs, if you're some asymptotic observer and you see only B, which is half of the Bell pair, then the entropy of that is greater than 0, because each particle that's being emitted is thermal. Okay? So we have three rather robust statements. This statement comes from the Page curve that I showed you previously. This statement comes from the statement that the horizon is locally like flat space, and the black hole is emitting Bell pairs. And this statement comes from the fact that Hawking radiation is thermal. So it looks like we have three rather robust statements. But these statements are in contradiction with a very general theorem called the strong subadditivity of entropy, which says that if you take any three distinct systems, A, B, and C, then it's the case that SA plus SC is smaller than or equal to SAB plus SBC, and you see you clearly have a violation here, because SAB is smaller than SA, SBC is 0, and SC is greater than 0. Okay? So it looks like not only do you have a violation, you have a violation at order 1, because SAB is smaller than SA by some factor of log 2, SC is log 2, if you think of just Bell pairs being emitted, and SBC is 0, and so it looks like you have some violation of this with 2 log 2. So it's not some violation at some order 1 over n, it looks like it's an order 1 violation. Okay. Yeah.
So, I mean, why is it, you say you only have to assume that the Hawking radiation is thermal at order 1. You don't need to assume
That's
that.
right. That's right. So it's just a statement about this. Okay.
These are all functions of t.
These are all functions of t. So you can evaluate this at any given point in t.
So SC is well defined.
But so the way I'm thinking of, so the way you should think of this, I'll try and make this more precise if you like, is that you think of an emission of Bell pairs. So SC is the Bell pair that's being emitted at time t. So you should think of Hawking, to get this paradox, you have to think of Hawking radiation as a discrete process where you're emitting particles at each time. So SC is the entropy of the particle, or is the von Neumann entropy of the particle that was emitted at time t. SAB is, SA is the entropy of the radiation outside at time t.
I thought C corresponded to particle inside.
That's right. So sorry, SC is the same as SP. So this is A, this is B,
Lights.
and this is C. That's right. But SB is equal to SC in some finite number. Let me set it to log 2. And the reason SB is equal to SC is because SBC is 0. If SBC is 0, then it must be the case that SB is equal to SC. And SBC is 0 because these two particles are together forming Bell pair. Any question?
I mean, this all seems very slick, because, I mean,
I'll
I would
make
worry
this
about,
more
I don't know how to, do I have to extend my time foliation inside the
precise.
black hole?
I'll make this more precise.
All the
I'll
time?
make this more precise. I'll come to more precise correlations. But so for now, think of particle. Think of Hawking radiation as happening by emission of Bell pairs. I'll make this more precise. At that level, there's a paradox. You can try and make it. You can try and think of these packets which are being emitted to make this more precise. But I'll give you a more precise version of these paradoxes. So by the end of this, I'll make everything precise. In any case, I actually want to say that this is also not such a significant paradox, because you can can resolve this by recognizing that there are limits on bulk locality. And these limits on bulk locality are things that are important. And although it looks like an order 1 paradox, it's in fact not an order 1 paradox. And that's because you have to recognize that, in quantum gravity, there's no natural distinction between these systems A and B and C. Of course, there's a sense in which low-point correlators look like they're local correlators. You compute, 2-point correlators of functions here and of functions here, and they look like they're totally different. But there's no fundamental, way in which you can divide the Hilbert space into an A and a B and a C. Okay? And this just the fact that there's no fundamental division of the Hilbert space into these 3 parts. So this is cobweb is one way of picturizing this, which is to say that the degrees of freedom of the black hole far away, or the degrees of freedom inside the interior, are some scrambled version of the degrees of freedom of the black hole far away. And just if you recognize that there's no way to divide the Hilbert space into parts that factorize, one part corresponding to one region and another part corresponding to another region, you find that you can resolve this paradox. Because in such a situation, if A, B, and C don't all live in distinct Hilbert spaces, then the strong subadditivity of entropy doesn't apply. More precisely, this is the following statement. I'll give you a more concrete example tomorrow. It's a statement that you take this black hole, which is formed by the collapse of a star, and you take 2 points, one inside and one outside, and you compute the commutator of these 2 points. And this commutator happens, it's a commutator on what you might think of as a space-like slice, is 0 within its expectation value of 0, and it's also 0 provided you within low-point correlators. So you take this commutator and you try to measure it by inserting 3 or 4 other fields, or 10 other fields, or 100 other fields, and all these correlators are 0, but C is not 0 as an operator. And if you could measure C to order e to the minus s, or if you could measure an s-point correlation function, then you would see that C is not 0. And just the fact that C is not 0 by this tiny amount, that there's this very small loss of locality, extremely small loss of locality, which is extremely hard to see between inside and outside, is enough to resolve the strong subadditivity paradox. And the reason it's enough to resolve the strong subadditivity paradox goes back to the point I made earlier, which is that the entanglement entropy is actually a very fine-grained observable. The entanglement entropy is not a coarse-grained observable. And that's because you can take 2-density matrices which have the property that all their correlation functions are the same up to e to the minus s, but their entanglement entropies are different at order 1. Okay? So really what you did in the strong subadditivity paradox is you thought you had an order 1 contradiction, but the order 1 contradiction involves quantities that are fundamentally fine-grained quantities, and that and therefore if you have a very small loss of locality between inside and outside, then that's enough to make this not a good observable, and enough to not make the strong subadditivity paradox a good paradox. And therefore this paradox, I claim, is also resolved by recognizing the limits of bulk locality. I'll give you a more concrete example of this resolution tomorrow, but I just want to say that this is not a very good paradox either. Yeah. Question? Is there any question about this? So this is the thing that people tend to think about the most when they think about the firewall paradox, which really is the weakest argument for the firewall. Okay, so now I want to come and talk. So I want to talk about what I think is a good paradox, and I would call this the modern information paradox. And this is really, I think, the contribution of AMS and AMPSS. And what AMS did, in a sense, is they pointed out that you can rephrase the information. I mean, a lot of this was inspired by the work of Mathur, and their first papers also talked about the strong subadditivity of entropy. But if you look at the later papers with AMPSF, also Naros and Polchinski, who have a sequence of papers on this, they pointed out that you can rephrase the information paradox in terms of low-point correlators without making any reference to these fine-grained degrees of freedom, entanglement entropies, and other such things, which could be, while it could all stop making sense if you had very small violations of locality in a semi-classical space-time. Okay. So now I'm going to shift gears a little bit. As you said, I was trying to say things. Everything I said so far might have been a little stick, but I'll try and make things more precise now. So these, and that's because these paradoxes are precise. I think there isn't so much point in trying to make the previous paradoxes precise because they're easier to resolve. These paradoxes, I think, are more precise and they're much more subtle to resolve. And so I'll talk about them now. All of these paradoxes are framed within the context of AdS CFT. So I'm going to switch gears and I'm going to talk about AdS CFT, And well, of course, you describe the dynamics in the bulk of AdS in terms of some holographic conformal field theory. And I'll also start talking about big black holes in AdS, which are black holes that don't evaporate. And as you will see, even the fact that black holes evaporate is not necessary to frame the information paradox. So the main things that I'm going to need about the CFT, I'll need some rather generic properties. And you'll see that even these generic properties are enough to set up a paradox. And what I'm going to say is that you can define standard statistical ensembles in the CFT. There's a canonical ensemble, a microcanonical ensemble. These two things are equivalent, but usually equivalence of ensembles. And of course, the Hilbert space is finite dimensional, which is what you said some time back, and that's true in the CFT. So you take the CFT, you put it on S3 or put it on a sphere, and then you have the infrared cutoff. The Hilbert space is finite dimensional. There's a very high density of states at high dimensions, but that doesn't bother us. It's still finite dimensional. And of course, the dimension of the Hilbert space grows monotonically with entropy, grows monotonically with energy. Dimension grows monotonically with energy, not with entropy. Sorry. Okay. And of course, there's one more important element of the AdS CFT dictionary that I'm going to use, which is that if you take a generic state at high energy, if you take a generic state at high energies, then this generic state corresponds to a large black hole in the bulk. Okay, so this is something that we believe is true from many different calculations, including from counting of microstates. And so the idea is that you take a big, you take some very heavy state in the CFT with energy much larger than the central charge, and the bulk dual to this is a big black hole in AdS. So that's we think a robust element of the AdS CFT. Okay, now what is the claim of the modern information paradox, which I'll try and make precise? The claim is that there is no operator phi of x. Okay, there is no operator phi of x in the CFT, so that correlation functions of this operator phi of x in one of these very heavy generic states of the CFT are the same as the Green's functions computed in the black hole background using semi-classical effective field theory. So it's a statement that if you want that AdS CFT works and has a good dictionary, and you would like some way of describing bulk degrees of freedom, and the claim is that there is no operator in the CFT whose correlators in a typical state are reduced to the Green's functions that you get by doing bulk calculations. Okay. So this is the statement, and I'll try and point out how these paradoxes occur. And I'll say that, as I showed you, these arguments just involve the generic properties of the quantum gravity or the CFT Hilbert space that I did previously. And at this point, you might wonder, where the information paradox comes in. Now, I was talking about, black holes radiating and losing information, and you might wonder why I even call this the information paradox. But in fact, as I'll show you, this is really a question of unitarity versus effective field theory. Because effective field theory is what computes these Green's functions for you, and unitarity suggests that there's no operator that has these properties. As I said, I'll show you a resolution for it, but the paradox is this kind. Yeah.
Why do you want psi to be a pure state?
Why do I want psi to be a pure state? Because you would like that a generic pure state in the CFT corresponds to a big black hole in the bulk.
But would that be true if you start considering mixed states?
If you consider mixed states, well, if you consider mixed states, then the situation becomes better. You mean where the CFT is entangled with something else? So, if you take a thermal state, for example, then, that's actually, the paradoxes don't even occur for that. I'll show you how there's a paradox for the eternal black hole. But, okay, I'll say a little bit about mixed states. But for mixed states, the situation looks, prima facie, it looks better than it is for pure states. So, really the question is whether pure states in the CFT typical pure states in the CFT correspond to big black holes in the bulk. And we would like that to be the case, yeah. Any questions too?
Sorry, if you take that to be an exact equality, then that's still kind of a straw man. I mean, nobody.
No. Plus one over n. I'm happy if you can get it. So all this I want. There's no operator phi of x that satisfies the property plus 1 over n.
Good, but also how uniform in the energy. So even at sufficiently high energies, you don't expect it to even be 2 in order 1.
Well, at sufficiently high energies, you expect to get a bigger and bigger black hole.
You
make the energy bigger and bigger, and you expect to get bigger and bigger.
No, I mean the energy of the external insertions, not of the black hole.
Oh yeah. So these are. I'll just talk about 2-point functions in fact. You mean these insertions phi of x?
Yeah.
So I'll just talk about 2-point functions.
Oh, okay, but still.
So just 2-point scalar operators. So
but for energies that are low compared to the black hole.
Yeah, I can smear them out. Absolutely, I'll smear them out and make everything low compared to that. I'll talk about modes which are actually at the energy of the Hawking radiation, so much lower than that, 1 by n. So no gravity actually. Yeah, these are very good, yeah.
What do you mean by a generic state?
A generic state is again a state, you take a state at very high energy and pick a state using the Hahn measure. So you have some Hilbert space at CFT.
So high relative to
The central charge.
central
So you can take it 10 times, 100 times the central charge. Whatever the regime of the CFT, it corresponds to a big black hole. It's generally order 1 times the central charge, but order 1 is a large number. So large number in the central charge. So any other questions?
So define the local field in the back of the foundation.
But the claim is that there is no operator in the CFT that can play the role of a local field in the bulk. You would like that there should be some operator in the CFT that can play the role of local fields in the bulk, but the claim is that there is no such operator that can do the job.
So the coordinate restricts to the boundary or?
The left-hand side is a boundary statement. It's a statement that it's a lack of existence claim. So that there is no operator phi, which has the property that is correlators when computed in the generic state. And this is a bulk calculation. You get these Green's functions by doing a bulk calculation.
But all the x1 to xn are restricted to boundary or they are also?
No, x1, xn are bulk. So you explicitly want them to be in the bulk, and some of them should be in the interior as well. But the point is that even though the CFT is a local CFT in d dimensions, you expect that there should be some operator in the CFT that's dual to a local field in the bulk, which you can always label by an extra by an extra coordinate. So this is not a local operator in the CFT. I'm not saying this is a local operator in the CFT. Any operator, I'm happy to find any operator.
So with this case, probably a stupid question, but don't you want some entropy associated with the state?
With the state? Entropy associated with the state?
Yeah, so as to correspond to.
No, I don't think so. I think you really like a generic. When you count microstates, you're really counting the number of pure states. And when you do the Stromdil-Waffer calculation, what you're saying is there are e to the s states of this kind, and that's what corresponds to the entropy of the black hole. There's an entropy corresponding to the black hole, but each individual state is a microstate of the black hole. So
then why are you comparing it with the semi-classical computation?
Because a microstate of the black hole looks the same as a black hole. You see, you have a black hole. The black hole could be in a given microstate. The microstate is a pure state, and the reason it's called a microstate is because for a semi-classical calculation, it looks the same. If you look at you see a black hole in the universe. The black hole is in some particular microstate, but the external geometry and low point correlators are the same. That's why they're microstates. They're microstates because they differ microscopically, but for these Green's functions you do get using effective field theory, they do not differ. Okay, very good. So let me now say. So the main thing is that you have to recognize. So the second important point to recognize is that to describe a local field inside the black hole, you need both left and right movers. Okay, and this is just a property of solving the wave equation. If there is any such field that has to exist that has to reproduce these Green's function, what you'd like is that this field should satisfy some wave equation. And if you just solve the wave equation, you find maybe you can't see in the back. I'm sorry about that. You find that you get. I'll just draw it here. So it's this is the horizon. You find that your field outside looks like some modes into e to the I omega into r star plus e.
Suvrat, can you turn on the lights?
So yeah. Let me put it this way here because I'm dropping factors of 1 over root omega and other such things. This is just a property of wave equations in the black hole background. If you solve a wave equation in AdS outside a black hole, you find that normalizability at the boundary, you should quantize fields in terms of normalizable modes. Normalizability at the boundary fixes modes which, the left and right movers means whether they go in terms of the tortoise coordinate in the time, whether they move to the left or the right. So these are what I would call right movers. R star minus t terms, okay, and these are what I call left movers. So left movers are modes that continue smoothly past the horizon, and so this is the same, okay, and these are new modes. Now, those of you who've seen Hawking's calculation are familiar with these modes. These are the modes that Hawking computed by having bounced off the origin of polar coordinates. So, when Hawking computed these modes, he found these blue modes and he analyzed them by tracing them all the way back to the past and by saying that they came by bouncing off the origin of polar coordinates. And that's these A tilde omega modes. And there are many other ways you can see them. If you think of, you can think of these modes as coming from the left asymptotic region of the eternal black hole. So if you think of the eternal black hole, there are modes that are left movers that have support on the right boundary, and there are modes that are right movers, that are these blue modes, which have support in the left boundary. So you can think of these modes in various ways, but whatever way you think of them, if you just solve the wave equation, you find that there are these two solutions, and if you want some operators to play the role of these local fields, it must have these modes corresponding to the left and the right movers. Okay. So now, here's what I want about the short distance correlators. I said Green's functions is computed in the black hole background. In fact, I'm going to use a very simple property. All I'm going to say is that you take this bulk field and you compute its Green's functions, its correlators in a typical state. And if you take x1 going to x2, just the short distance behavior of these correlators, and the short distance behavior should be given by the geodesic distance. Okay, and that's a very robust property which all of us will agree should be true of any quantum field theory. And you take the short distance behavior, as long as it has some ultraviolet free fixed point, its short distance behavior is given by the geodesic distance raised to some power. Okay? And you can translate this into the statement into Kruskal coordinates, just a statement about Green's functions. You take two Kruskal points, and you have to differentiate the fields, and you take, so u and v are the two different Kruskal coordinates. So you take these points to be close along the line cone, and you find that this statement, that the short distance correlator is given by the geodesic distance, translates into this statement in Kruskal coordinates. This delta function in the transverse coordinates is sometimes what's called ultra-locality in light cone physics. So those of you who've seen these discussions of ultra-locality in light cone physics might remember this delta function. But in any case, there's some very robust statement you can make about what these Green's functions have to behave like. And the question is, can you find operators phi in the field theory that have this property? Okay. So you can Fourier transform these statements. I made in position space, and I hope we'll all agree they're very robust statements. And when you Fourier transform these statements, they turn into statements about the 2-point correlators of these A tilde and these A modes, and they turn into the following statements. They turn into statements that A tilde with A tilde dagger is the same as A with A dagger, just comes from Fourier transforming the previous statements. And that's the same as this Boltzmann factor, 1 by 1 minus e to the minus beta omega. And A tilde with A is also non-zero, and it has this funny factor of e to the minus beta omega by 2 by 1 minus e to the minus beta omega. Okay? And these, you have to find therefore CFT operators that have these 2-point correlators in typical states if typical states have smooth horizons. Okay? Because if they have smooth horizons, then they have the short distance behavior that we wanted, and you Fourier transform the short distance behavior, and you get the statement for 2-point correlators. Okay? I'm going to need one more thing, which is the commutator of the Hamiltonian. Now the commutator of the Hamiltonian is a question of how things transform into large diffeomorphisms. So it's a gauge-dependent statement. And I'm going to fix a specific gauge, and the specific gauge is fixed as follows. You jump in from the boundary, and you wait for a certain proper time. Or actually, you can send light rays back. You can jump along a light ray, and you can send light rays back to normalize your affine parameter. But morally, what you're doing is you're jumping in from the boundary at this point, and you wait for a certain proper time, and then you measure the field at that point. Okay? So that fixes the gauge in which I'm defining these local bulk observables. In fact, some of you at the beginning could have said, when I'm talking about local Green's functions, what do I mean? These are not gauge invariant quantities. And it's true they're not gauge invariant quantities, but I can fix a gauge, which makes them well defined. And this is what I would call right relational gauge. Okay, so you define things relationally with respect to the right boundary. So there's a certain point on the boundary. This projector makes things very faint, but there's a certain point on the boundary, and there's a certain proper time, and points in the bulk can be labeled by points on the boundary and a certain proper time. Okay. And if you use this, then you find that these modes, you translate this gauge statement into a question of the commutator of the EDM Hamiltonian with these modes. And you find that these creation operators A have precisely the properties that you expect of normal creation operators, in that they have negative energy. But these A twiddles have the wrong sign of the energy. So the A twiddle annihilation operator, you see, has a plus sign here rather than